Assalamualaikum and a very good day. This presentation is titled Application of Cold Plasma Treatment to Extend Shelf Life and Preserve Nutrients in Fresh Cut Fruits. It is a group assignment for the course Special Topics in Nutrition. In this presentation, we will discuss the principles, processing steps, and effects of cold plasma treatment on fresh cut fruits. This presentation has been prepared by our group members, Aina, Nasuha, Shuhaida, and me. I will begin by introducing the background of fresh cut fruits and the principles of cold plasma technology. Fresh cut fruits are minimally processed, ready-to-eat fruits such as apple slices, melon cubes, papaya, and pineapple. They are popular because they are convenient and nutritious, especially as they are high in vitamin C. However, the cutting process damages the fruit tissue and exposes it to oxygen and microorganisms. This leads to increased microbial contamination, oxidation of vitamin C, and a much shorter shelf life, even when the fruits are stored under refrigeration. Therefore, effective preservation methods are required to maintain both safety and nutritional quality in fresh cut fruits. Cold plasma is a non-thermal food processing technology that has gained attention as an alternative preservation method. It is produced by partially ionizing a gas such as air or oxygen using electrical energy at near room temperature. Because cold plasma does not rely on high heat, it is suitable for heat-sensitive foods like fresh-cut fruits. Compared to thermal treatments or chemical sanitizers, cold plasma can reduce microorganisms while minimizing nutrient loss and avoiding chemical residues. The effectiveness of cold plasma is mainly due to the generation of reactive oxygen species and reactive nitrogen species, known as ROS and RNS. These reactive species damage microbial cell membranes, proteins, and DNA, leading to microbial inactivation. Since cold plasma generates minimal heat, it helps preserve heat-sensitive nutrients such as vitamin C. In fresh-cut fruits, cold plasma acts mainly on the surface, where microbial contamination occurs, allowing the fruits to maintain their color, texture, and overall fresh quality.
Cold plasma helps in bacterial inhibition. Plasma-activated water, which is derived from cold plasma, has a strong antibacterial properties. It can inhibit harmful bacteria such as Staphylococcus aureus and is more effective than UVC and aqueous ozone in controlling spoilage bacteria such as Botrytis cinerea. This helps improve food safety and reduce spoilage. Next, cold plasma helps in delayed microbial growth, especially when combined with low temperature. At low temperature, around 5 degrees Celsius, microbial activity slows down. This reduces biochemical and metabolic processes, which allowing the product to last longer compared to storage at higher temperature. Lastly, cold plasma helps with nutrient retention because it operates at low temperature. It reduces nutrient loss, especially vitamin C. As a result, the nutritional quality of the food is better preserved during storage. Overall, cold plasma is an effective non-thermal technology that improves food safety, extends shelf life, and maintains nutritional quality.
This slide shows the basic process of cold plasma processing applied to fresh cut fruits. First, the process starts with sample preparation. Fresh fruits are selected and then washed, cut, and any excess moisture is removed. This step is important to ensure uniform treatment and to reduce contamination before plasma exposure. Next is the selection of the cold plasma system. Different systems can be used, such as the electric barrier discharge, plasma jet, corona discharge, or microwave plasma. These systems generate cold plasma at low temperatures, which makes the technology suitable for heat-sensitive foods like fresh-cut fruits. The third step is carrier gas selection. Common gases used include atmospheric air, nitrogen, argon, or gas mixtures. These gases help generate reactive species in the plasma, which are responsible for microbial inactivation and quality preservation. Next, plasma parameter setting is adjusted. This includes controlling the voltage and power, frequency, treatment distance, and gas humidity. These parameters are important because they influence the intensity of the plasma and the effectiveness of microbial inactivation while minimizing damage to the fruit. Next is the cold plasma treatment itself. The treatment can be applied neither directly to the fruit surface or indirectly depending on the system used. The exposure time is usually short, ranging from a few seconds to several minutes, which helps maintain the fresh quality of the fruits. Finally, the fruits undergo storage and evaluation. They are typically stored under refrigerated conditions, and their quality is assessed by measuring microbial reduction, enzyme activity, and changes in color and nutrient content. This evaluation helps determine how effective the cold plasma treatment in its extending shelf life and preserving fruit quality. Overall, these steps ensure that cold plasma treatment is both effective and safe for fresh cut fruits.
Nutrient retention in fresh cut fruits depends on treatment conditions, fruit type, and storage. Cool plasma is a non-thermal method that reduces heat-induced nutrient loss. Short treatments can effectively inactivate microbes while preserve nutrients, but prolonged or high-intensity exposure may cause oxidative damage. These compositions also plays a role. Oxygen-rich plasma includes antimicrobial effects but can degrade nutrients, while optimized gas mixtures help in preserve them. Fruit characteristics such as skin thickness and moisture influence nutrient stability, and post-treatment storage can further affect nutrient level. Careful optimizations of cold plasma for each fruit types help maintain both food safety and nutritional quality. For industrial applicability, cold plasma kills microbes without heat and keeping nutrients and quality intact. It fits into existing line and supports large-scale and chemical-free processing. For limitations, high cost and variable effectiveness limit adoptions. Non-treatments can affect texture, color, and flavor, so combining with other methods may help. For consumer and market acceptance, consumers accept cold plasma more when benefits like safety, shelf life, and nutrients are explained. Clear labeling and education build trust, and demand for high-quality fruit support its use. Cold plasma is a non-thermal technology that extends shelf life and preserves nutrients in fresh cut fruits by inactivating surface microbes without heat damage. The process involves produce preparation, system and gas selections, parameters optimizations, treatments, and quality evaluation to ensure safety and quality. Nutrient retention depends on treatment intensity, fruit type, and storage. Optimized conditions preserve nutrients, while overexposure may cause oxidations. Nutritional quality, especially vitamin C and sensory attributes like color and texture, are generally maintained under proper conditions. Cold plasma is more effective than UVC on complex fruit surfaces, but high cost and process variability remain challenges, which can be addressed by combining it with other non-thermal technologies.